Sorry about that. Let's get back to where we were. So here we have magnesium sulfate. We have a +2 and a -2 charge, so that is balanced, at least the compound. We'll balance everything in just a moment. And then we have our sodium chloride. Here we know we have 2 chlorines on the left and 2 sodiums on the left, so if we add a 2, we're all good and done. And so the question becomes, is this a solid or is this aqueous? And so in this case, sulfates are always going to be soluble, one of the rules that we use. And with the exception of, say, things like calcium and some others, but magnesium in this case makes it soluble as well. And so we actually have what we considered there to be no reaction in the case where technically they could swap, but because they are both soluble, a better way to represent this might be, for example, with some of our ionic equations. Right? Because they're soluble, they never stick together, and so they're going to end up being just kind of like a soup of all of those ions. We could imagine seeing it this way as well. And so there is no precipitation for what we have here. Let's look at another example of that. So here we have magnesium chloride and sodium nitrate. And so we're going to swap them, right? Here we're still going to get out NaCl. And we're also going to get out magnesium nitrate. We know that the nitrate is going to be -1, so we'll need a balance of 2 here. And we'll find, right, that there is actually no reaction here as well. Nitrates are always going to be soluble, at least in the purposes with magnesium, and so there is no precipitate, and each of these will be aqueous. And so we can think of it just like this last example as kind of a mix of all of the ions in solution. There's no solid that drops out. So last but not least, we have an example with our phosphate. And so let's look here, right? We know we're still going to flip them. And so, for example, we're going to get our sodium chloride out. In this case, maybe we'll start with the fact that it is aqueous. And then from here, we're going to look at what our products would be, right? And so we know that it's going to be a blend of magnesium and the phosphate. We have a -3 charge for each of these. We have a +2 charge for each of these. And so one of our tricks, right, is we can flip them. So we will have 3, and we will have 2 for the amount of phosphates and what we have here. Looking at those solubility rules, we're going to find that phosphates are going to be insoluble. And so here we have a solid product to contrast the aqueous product here, and we'll find that we do have a precipitate in the form of this magnesium phosphate. So that's just a couple examples of how we can begin to select and determine if we have precipitates from our reactions. Now let's begin to look at some examples from Chapter 5, which we're jumping into, and we'll begin to see some of the redox properties of some of these similar equations. Okay, so actually not precipitations. We're going to be looking at other types of reactions in aqueous solution, but there may be some. So these are going to be, in part, some redox reactions. And let me think of a couple good ones to do. Let's do a reaction between iron metal and hydrogen chloride, or hydrochloric acid, I should say. Let's also do one between iron and then also a copper sulfate solution. Right, so a strong acid, a probably strong electrolyte in the example we're using. And then let's do one between, say, an iron salt, and then also, in this case, we'll do a strong base as well. And so know that if you want some good practice for these, is that there's really a finite number of combinations of things we can work with, right? A weak acid, a strong base, you could have a strong electrolyte and metal, for example, and so you can begin to practice and see what does come out. And in theory, if you've gone through them all, by the time you get to the exam, you'll kind of know what to expect. It might just be a different element, but the same principle there. Okay, so let's think. This is kind of new to us, but one of the things we know that's going to change is going to be the oxidation state. So let's examine this first one, and then we'll begin to look at some of the details in the others as well. So one of the things we find when we react iron in this case with hydrogen chloride or hydrochloric acid is that we're going to get out an aqueous or soluble mixture of iron chloride, and we're also going to get out the hydrogen gas. And so in this case, right, we're going to have essentially a product that's going to bubble out, and then the reaction is going to go all the way forward. Something we note, we have 2 of the chlorines and hydrogens on each side, and so to balance this, we would need a 2 as well. And to be good, let's add in the aqueous here, and then iron, no surprise, is a solid, right? Just like most metals in that way. And so let's examine this just a little more. What is the charge and then also the oxidation state on the iron that we have here? Well, we know that the total charge for this compound is 0. And so we know that, for example, the iron must balance the -1 chlorines, and there's 2 of those. So here we have our iron in the +2 state, which here will also represent the oxidation state, or the oxidation number, you might say. And so here we can see that we've gone from an oxidation state of 0, and yet, say, the hydrogen's still +1 and chlorine's -1, so those haven't changed. So again, we can say that the oxygen has lost electrons, it's become more positive. A loss of electrons is oxidation in this case, so the iron has been oxidized. Similarly, in this case, the hydrochloric acid is our oxidizing agent. And generally, we find when you come out with hydrogen as a product, you're going to have some oxidation that occurred. If you add hydrogen in, you might have a reduction, for example. There was one more thing I wanted to say, and it's escaping me very quickly, but I think that that's okay. I guess just that, again, how did I know a loss of electrons is oxidation? I always like to use, again, Leo the lion, and so he's going to help us out here, no surprise. And so now we not only have the answers to our equation, but we also have a pretty good understanding of what's going on, right? This is an oxidation reaction. There's a change in the charge and thus oxidation state of each of these individual, well, ions, I guess, only here. Okay, so now let's look at what happens if you take iron metal and react it with copper sulfate. Here we're going to find, again, that sulfates are very good at dissolving. They're good electrolytes. And so here we're going to have an aqueous solution. Let's look at our products here. Here, instead of having a double replacement, right, there's nothing else for iron to be with. It's not going to swap anything else. It's just iron. We're going to find that the iron and the copper will swap in this case. And so here we're going to have iron sulfate as one of our products. And then we're also going to have copper. Here we will see that this sulfate is still soluble, right? So really what we've done is we've taken solid iron and put it in solution, and we're going to take the copper and we're going to make it a solid. And so how did I know that copper was a solid here? Well, again, let's look at those oxidation states, right? Iron, to start, is going to have an oxidation number of 0. All free elements and atoms will. In this case, we'll find that copper is going to have a +2 charge to balance that -2 charge, and this will also be the oxidation number. And so let's figure out what it is over here, right? Copper by itself is going to be 0. And then iron, in this case, is again going to balance that sulfate, and so we can see that it's that single replacement in terms of that charge and that placement as well. And so here we're going to have a +2 oxidation number. And we can see again, right, that iron in this case lost a couple electrons, same charge as we had before. And so the iron is oxidized. And in this case, we have our oxidizing agent. We can also see that the copper's been reduced, right? We have gained electrons. We've gone from +2, added 2 electrons in to balance that charge to 0. And so we have a total charge, in this case, to let us at our base metal. Okay, and you guys have been doing pretty well. I don't have a watch on, but I know you have. Let's do one last one, and then we'll begin to see. So here we have iron chloride, and we have the sodium hydroxide. Let's actually start, in this case, with the oxidation states, and we'll see if anything changes. So we're going to have the +2 here, and we're going to have the -1 for each of those, -2 total. Here we're going to have a charge of +1 and a charge of -1 for the ion, right, this whole thing. But let's look, the oxygen here is going to have an oxidation number of -2. That's one of our rules. And then the hydrogen here is going to have one of +1, right? -2 and +1 will give us the -1 for the entire ion there. And so here we find it's not really so much a question of redox. Here we're going to find that it's just, again, a question of that double replacement. And so, for example, we're going to get out an iron hydroxide. We'll balance in just a moment. And then we'll get out, no surprise, our sodium chloride, which we know to be aqueous. So first we can see, right, we have 1 chlorine on the right and 2 on the left. So we'll add a 2 for each of these. And then if we add a 2 for the sodium, we can see we now have 2 hydroxides as well, which makes sense. When we begin to look at the oxidation state of that iron, or the charge as well, we're going to find that it is still +2. So here we have no oxidation or reduction, right? Was +2, remains +2, and sodium generally isn't going to be easily oxidized or reduced, at least in these examples. And so we'll find that there's no change there. And so something else we'll find is that this is really just a good example of a precipitation reaction. We find that hydroxides generally are insoluble, except in cases where you have a group 1 metal, like sodium. And so really what we've done is we've traded out something, we formed a solid, the hydroxide here, and at the end of the day, no redox, right? Just thinking kind of about acid-base chemistry a little bit, or that double replacement, again, we call metathesis. And so I think that that's going to be good for today. I'll be doing a couple more of these as well, so let me know if you like them. Otherwise, I think that things are going pretty okay in the course. Let me know if you disagree. And I guess I'll see you guys soon. Have a great week.